We previously talked about Lewis structures, and we've also talked about shapes of molecules. So these are old. And so the new things I want to talk about is bond polarity and having a polar molecule. But in a sense, in order to see if you have a polar molecule, first you have to be able to do a Lewis structure. Then you have to do the shape. Then you have to determine if there's polar bonds. This is not necessarily a hard skill, but you have to be able to do the previous skills in order to decide if you have a polar molecule. And so we define electronegativity as the ability of an atom to attract bonding electrons. So a difference in electronegativity between the atoms in a covalent bond results in the polar covalent bond or increased ionic character. The difference in electronegativity, the greater the ionic character and the more polar the bond. No difference in electronegativity between atoms in a covalent bond results in a non-polar covalent bond. The electronegativity scale tells us which elements have a greater pull on electrons in a covalent bond. The more electronegative element pulls bonding electrons more strongly and obtains a partial negative charge. The less electronegative element loses electron density in the bond and therefore obtains a partial positive charge. They're showing a hydrogen fluoride molecule. And so the hydrogen's one electron will share a bond with the fluorine. Forget about the lone electrons over here, but in the bond, the electrons are pulling closer to the fluorine. The fluorine has many, many more protons, and it has a fairly exposed nucleus. So it's going to pull the electrons in the bond toward itself. If the electrons in the bond are more toward the fluorine, then the fluorine counts as having an extra electron 80% of the time. Depends on how uneven the sharing is. The electrons in the bond get to be around the hydrogen only 20% of the time. So in a sense, the hydrogen is losing electrons. So it's not a full gain and loss like an ionic bond, like in sodium and chloride. The sodium gets a full positive charge and the chlorine gets a full negative charge, right? The sodium completely lost the electron, the chlorine completely gained it. So that's what we call an ionic bond. But here, this is a polar bond, right? They're sharing unequally. So they have a covalent bond because they're both nonmetals. But the electrons are spending most of their time around the fluorine. So the fluorine gets this partial negative. This funny symbol here is a lowercase delta. So the fluorine gets a partial negative charge and the hydrogen gets a partial positive charge. And so in order to do this on a test, you will have to be given an electronegativity scale. And so, most of the noble gases are excluded. You'll see some of the lower ones is kind of interesting. Krypton and xenon actually have electronegativity. They can make bonds. So that's actually a newer development. The highest up here, the fluorine, gets a 4, right? And that's the highest on the possible scale. And then the lowest down here, the very down and to the left would be francium with a 0.7. You see these yellows. Basically, what it means to be a non-metal is having a high value for electronegativity. They have a much stronger pull toward electrons in a bond, right? And the metalloids all have green values, right? They all have these kind of intermediate electronegativities. And all of the metals shown in the aquamarine and blue have lower electronegativities. And so again, the trend is up and to the right. To determine the polarity of a bond, you calculate what we call the delta, this is capital delta now, the delta electronegativity. And the delta electronegativity is equal to the absolute value of the difference in electronegativity. So electronegativity 1 minus electronegativity 2, and then absolute value. You guys remember, what does absolute value mean? You guys remember how to do that?
Means you get a positive number.
It's always positive. That's correct. Okay, let's look at some bonds. What if we have it? So let's not worry about Lewis structures. Just to say we have a carbon-nitrogen bond, right? And carbon on the electronegativity scale that we've been given is 2.6. And nitrogen is 3.0. This delta electronegativity of this bond would be equal to the absolute value of 2.6 minus 3.0, which would be what?
0.4.
0.4. Okay, so that'd be 0.4. We can do some other ones. Let's do carbon,
Okay.
chlorine. So carbon, again, it's always going to be, the atom is always going to be the same. Carbon's always 2.6. Chlorine's 3.2. So what's the delta electronegativity there? 2.6 minus 3.2. Okay, so this would be 0.6. Let's do one that's really extreme. How about sodium and chlorine? Pretend like there's a bond. We know it's an ionic compound, though. But sodium is 0.9, and chlorine, again, is still the same as 3.2, right? So this would be 0.9 minus 3.2, so 2.3. Okay. Nitrogen, fluorine. So fluorine is 4.0. Nitrogen is 3.0. What's the delta electronegativity?
1.
1. So if the delta electronegativity is 0 to 0.4, this is what we call nonpolar. And that means the electrons are shared equally. So if the delta electronegativity is 0.5 to 2, then it's polar. And so that both of these, the nonpolar is covalent, right? So it's sharing electrons. And this 0.5 to 2 is polar covalent. Let me put a little caveat here. Unless metal with a nonmetal. Then the delta electronegativity, if it's greater than 2, then it's ion, right? Like sodium and chlorine. Unless it is a nonmetal with a nonmetal. So that kind of the nonmetal with a nonmetal and the metal with a metal rule kind of trumps this range. There we are. So now we can go back and look. Carbon-nitrogen bond, nonpolar. This carbon-chlorine bond is polar. The sodium chloride bond is actually ionic. The nitrogen fluorine bond is polar. And so also, by the way, so this 0.6 would be, somewhat polar. This 1.0 would be this would be more polar. Maybe I can underline it. That's a very polar bond, meaning the sharing is much more unequal here than it is here with the 0.6. It's a little less polar, but it's still polar. Nonpolar is anything with itself. So that's kind of an obvious case. If you have N2 or F2 or H2, those bonds, what's the delta electronegativity of hydrogen with hydrogen?
0.
It's always going to be 0. Delta En equals 0, whatever this value is. So hydrogen's 2.2, hydrogen's also 2.2. So at 0, that's automatically going to be nonpolar. Other things that tendencies, so carbon-hydrogen bonds are going to be nonpolar, right? Carbon is 2.6 and hydrogen's 2.2. So that's 0.4.